In the age of steam, engineers chased the impossible, a locomotive that could cross deserts without ever stopping for water. The locomotive that could run forever. Britain's underground ran miles beneath London thanks to recycled steam. In South Africa, one engine covered 1,000 miles before maintenance chaos set in. So why was forever just out of reach? In the heart of Victorian Britain, the Great Western Railway set out to solve a problem that plagued every steam railway: water. Between 1862 and 1869, GWR engineers built a series of experimental engines equipped with condensing gear, an early attempt to capture spent steam, cool it in tanks, and feed the water back into the boiler. These broad-gauge prototypes carried bulky radiators slung beneath their frames, their pipework twisting beneath polished brass fittings. The goal was simple: stretch each drop of water as far as possible, especially on routes where supply was scarce or refilling meant lost hours. The London Metropolitan Railway, opening its first tunnels in 1863, faced a different challenge. Underground venting clouds of steam into cramped, poorly ventilated stations was a recipe for disaster. The Metropolitan Class A and B locomotives, introduced from 1864, ran with their own condensing systems. Exhaust steam was piped into long side tanks where it cooled and condensed, keeping tunnels clear, or at least clearer, of choking vapor. Crews worked in stifling heat, their cabs often hotter than the boiler itself, as they coaxed the engines through the labyrinth beneath the city. Condensing gear promised water savings and cleaner air, but it came with a price. The machinery added weight and complexity, and oil and soot from the cylinders fouled the recycled water, turning maintenance into a daily battle. Underground crews learned to dread the sticky residue left in tanks and pipes, while surface engineers logged extra hours cleaning, flushing, and patching leaks. Even so, these first practical condensing locomotives showed that the dream of endless steam was more than fantasies. It was a challenge engineers were willing to meet, one experiment at a time. Across the arid stretches of the Karoo, the South African Railway's Class 25 condensing locomotive became an unlikely champion of endurance. Introduced in 1953, these engines could travel up to 700 miles, sometimes more, between water stops, a feat that turned heads in railway circles worldwide. The secret lay in their massive Type CZ tenders, bristling with radiator tubes and fans, designed to reclaim and recycle nearly every drop of steam. On a typical run, water consumption dropped by about 90% compared to conventional locomotives, a difference that meant the line could cross deserts where tankers once stood waiting every few dozen miles. Crews who worked these engines remember the pride of pushing a single fill across half the country, but also the price paid in the sheds each night. Workshop foremen logged hours, scraping oily sludge from condenser tubes, flushing scale from the labyrinth of pipes, and coaxing seized turbine blowers back to life. Maintenance records from the 1960s show that keeping a Class 25 condenser at peak performance demanded up to 40% more workshop time than its non-condensing cousins. Bearings wore quickly under the constant strain, and recycled water, thick with grit and oil, fouled boilers in ways the designers never fully solved. By the early 1970s, with diesel locomotives taking over and water supplies improving, the railway began converting most of the fleet to simpler, non-condensing Class 25 NCs. Between 1973 and 1980, 87 engines lost their condensers and gained larger tanks, their long, sausage-shaped tenders earning the nickname Worschend. The ambition to run forever had delivered on distance, but not on simplicity. In the end, the desert's greatest steam experiment proved that every solution carries its own cost. At the Darlington Works in 1929, a team led by Sir Nigel Gresley and Walter Wilson set out to break the pressure ceiling that had held back steam locomotives for decades. The result was the LNER W1, known among railwaymen as the Hush Hush. Its water tube boiler, inspired by marine engineering, was designed to run at 450 psi, nearly double the pressure of most mainline engines of the era. In theory, higher pressure would mean more power from less fuel and water, pushing the limits of efficiency far beyond what condensing systems could achieve. But the reality inside the shops was less forgiving. Workshop records revealed that the W1 spent 1,105 days out of service for repairs and modifications, more than 3 years of its short life. Persistent leaks, overheating, and joint failures dogged every trial run. Gresley himself admitted uncertainty about the locomotive's reliability, pressing for more safety trials as the engineering team struggled with the limits of steel and sealing technology. The W1's legacy became a warning. Chasing ever higher pressures demanded materials and workmanship that the era's factories could not consistently deliver. The dream of endless motion was now tangled in the hard facts of physics and metallurgy. Turbine power promised a cleaner, smoother answer to steam's old problems. In the mid-1930s, British engineers at the London, Midland, and Scottish Railway unveiled the Turbomotive, a locomotive driven not by pistons, but by a spinning steam turbine. The theory was enticing. Turbines could turn steam's energy directly into rotary motion, eliminating the hammer blow and wear of reciprocating parts. At cruising speed, the Turbomotive ran almost silently, its drive as steady as an electric motor. Designers in Sweden, led by Fredrik Lundström, took the idea even further, exporting their turbine locomotives to Argentina and across Europe. But the smoothness of turbine drive came with a catch. Turbines thrived at constant high speeds, perfect for express runs, but ill-suited to the stop-start rhythm of most railways. Every time the schedule demanded a slow crawl or a sudden burst of power, efficiency nosedived. Speed efficiency curves from the Ljungström trials showed dramatic drops outside their narrow sweet spot. Crews found the locomotive sluggish on gradients and wasteful in yards. The LMS Turbomotive served for 14 years, from 1935 until its destruction in a collision in 1949, but never inspired a fleet. The promise of endless, effortless motion faded against the reality of railway duty cycles. Turbine power, elegant in theory, stumbled on the uneven ground of real-world railroading. In the late 1920s, German engineers set their sights on the next frontier of steam. Pressure so high it bordered on the unimaginable. The Schmidt-Hartmann high-pressure locomotives, developed between 1925 and 1930, were designed to run at 900 psi, triple the pressure of most mainline engines. On paper, these machines promised unmatched efficiency and range, holding out the hope that steam could finally conquer its own limits. But the reality inside the workshops was far more dangerous. Safety inspectors and engineering boards pored over failure reports as the first trial runs revealed a pattern of leaks, stress fractures, and slow corrosion eating away at vital joints. One catastrophic boiler failure sent a pressure vessel tearing through the roof of the test shed, killing several workers and forcing a government inquiry. Survivors described the sound as a cannon blast, followed by a rain of twisted metal. Regulators demanded a halt to further trials, and insurance underwriters refused to cover continued experiments. The project was canceled before the decade was out, its records sealed by the state. For a brief moment, ambition had pushed the boundaries of physics so far that every test run became a wager with fate. The Schmidt-Hartmann program stands as a stark reminder. The closer engineers came to perpetual motion, the more they risked unleashing forces beyond their control. Italian railway administrators, facing rising coal prices and the looming spread of diesel traction, turned to the Franco-Crosti boiler as steam's last hope for economic survival. These locomotives, introduced in the 1950s, promised to squeeze an extra 8 to 12% efficiency from every ton of coal by channeling exhaust gases through preheaters before venting them to the air. On the books, the savings looked real. Trial runs on the Rome to Naples line logged consistent reductions in fuel use, and technical memos from Ferrovie dello Stato confirmed an average 10% improvement over standard engines. But the numbers on the balance sheet told a different story. Depot records from Milan and Padova detail a steady stream of complaints as thick, low-lying smoke drifted across platforms and city streets. Communities along the main lines filed petitions about soot and visibility, while maintenance crews logged overtime scraping corrosion from the preheater tubes. Internal memos reveal mounting costs. Every hour saved in the coal yard was spent twice over in the workshops, cleaning out acid deposits and replacing fouled parts. By the late 1960s, as diesel engines rolled out across the network, the Franco-Crosti fleet began to disappear from the rosters. Withdrawal schedules show Class 6 83s and 743s retired between 1966 and 1971. Their promised savings erased by the relentless advance of simpler, cleaner technology. The verdict from railway accountants was blunt. Marginal gains in efficiency could not compete with the economics of dieselization. In 1953, South African Railways introduced the Class 25 condensing locomotive, capable of running up to 1,000 miles without a water stop. This fact marked the peak of efforts to build a steam engine that could, in theory, run forever. Yet every breakthrough, from GWR's early condensers, to the LNER-W1's high-pressure boiler, to the Franco-Crosti's 10% fuel savings, met new obstacles: increased back pressure, relentless maintenance, or dangerous risks at extreme pressures. Workshop records show the W1 spent over 1,100 days out of service, and documented failures ended the Schmidt-Hartmann closed-cycle experiments by 1930. Some technical reports remain restricted, and full maintenance logs for certain prototypes are still incomplete, leaving open questions about their day-to-day reliability. Today, principles like heat recovery and closed cycles are standard in power generation, but the steam locomotive's quest for endless motion was never fully realized on rails. The legacy is clear. These machines taught engineers the hard boundaries of physics and shaped technologies that moved far beyond steam.